Parker Solar Probe has been around since 1958 in some form or another, and now in 2018 we're getting ready to actually launch Parker Solar Probe. A lot of that has to do with the fact that getting something to the sun is actually really hard, and there's a lot of technology that needed to be developed in order to enable this mission. There are many enabling technologies. The solar arrays were very important, the autonomy was very important. One of the ones that was obviously also critical was the heat shield, and developing the technology to actually protect the probe at the sun. That titanium truss was also specially designed for Solar Probe. It's actually a really neat piece. It's a welded titanium truss that's about 4 feet tall, but it only weighs about 50 pounds. And the key there is we're trying to minimize the conduction between the heat shield and the spacecraft. So you want to have as little stuff there as possible. The Parker Solar Probe heat shield is basically one giant sandwich panel. And a sandwich panel is a lot like a honeycomb panel you find in a traditional spacecraft or on airplanes. You have 2 outer face sheets, and then you have a core. In this case, the 2 outer face sheets are carbon-carbon composite, which is a lot like the graphite epoxy you might find in your golf clubs. It's just been superheated. And then the inside is a carbon foam. So the Parker Solar Probe heat shield has a white coating that's on the sun-facing surface of this giant frisbee that's protecting the rest of the spacecraft. And that white coating was specially designed here at the lab in collaboration with RED and the Space Department, as well as the Whiting School at Johns Hopkins proper, to actually work at the sun. This was specifically designed for Solar Probe. And the concept is basically you'd rather be in a white car on a hot day than a black car on a hot day. It's just that it just knocks down the heat that much more. And so it's helping us stay cool at the sun. The particles of the corona are very hot, like 3 million degrees. However, they're very dispersed. It's not all 3 million degrees everywhere. It's a little hard to visualize, but think about when you are baking cookies and you have your oven and you can stick your hand in and your hand doesn't burn up. But if you touch something, then you'd burn yourself. So similarly, when we're actually at the sun's corona, we're not getting that hot because there's just not as much there. So the temperature is actually lower than the overall temperature of the particles that are at the corona. When we're at closest approach, the front surface of the heat shield will be at about 2,500 degrees Fahrenheit. The back surface of the heat shield will be about 600 degrees Fahrenheit. But then the spacecraft bus is basically sitting at 85 degrees Fahrenheit. So the shield is actually really keeping everything very cool. And that's most of the stuff on the bus. Additionally, there are a couple of instruments that are hanging out off the truss, and they will be hot like the heat shield, like SPC and Fields. Those are brave instruments sticking out in the sun. But everything else will be kept at that nice temperature, 85 degrees, so they can be working properly and giving all that great science data that we're so excited about. After working on this for 10 years, it is really a pleasure to see it kind of actually coming to fruition. To be one small part of this huge engineering team that is making science dreams come true is just amazing. I can't wait to rewrite textbooks and change the way we look at the sun forever. I'm a whole ball of excited, and I honestly don't know exactly how I'm going to feel at launch, but I'm really excited to pass this off to the mission operations team and see all the science data that comes down and just get to enjoy all that Solar Probe brings us.